Hi. This unit is going to be about logic and AGI. Now, in the early days of AI, logic was the fundamental paradigm for thinking about artificial intelligence. John McCarthy was a logicist, and first-order predicate calculus was the fundamental conceptual framework for thinking about thinking. Certainly since about 2000, for the last 20 years at least, in artificial intelligence, logic has been viewed as a kind of failed paradigm. It didn't work. What I'm going to do in this unit, though, is say that that's true. It didn't work. But we can't forget about it because it feels like we do have to solve it. So let me point out that analytic reasoning is still sort of dominant way software gets written. We're not about to replace compilers with GPT-3, right? There are people who try to write computer programs by sort of randomly writing some program and running it on a test case and doing random modifications until the test case runs without understanding, analytically what's happening and having an analytic understanding that this program is correct, right? So compilers themselves have very strong, very precise correctness notions. They're providing a certain model of what the program does to the programmer, and they have to be faithful logically, analytically to that model. And if we didn't have that, computer science as we know it would just collapse. And it's not just the compiler, right? The programmer thinks about whether this program is correct. There is a notion of bug. There is a notion of correct. And that analytic thinking is very similar to what happens in mathematics. People prove theorems. When you write code, you should be proving to yourself somehow that this code is going to do the thing you want it to do. If we're going to get to AGI, and I.J. Good's little statement about machines that can do anything people can do means that we have to get machines. If we're going to get to AGI, machines have to be able to do this. And GPT-3 is not close. Now, I'm also going to argue that there are phenomenon in language and common sense that really are sort of best understood through logic. So I'm going to talk a little bit about logic and common sense. And in particular, I'm going to talk about obviousness. Now, this is not saying that logic, I'm still admitting that logic failed, back in the 60s and 70s. But I'm saying also that there are phenomenon that point toward the existence of logic in human thought. So I'm going to focus on the notion of obviousness. Certain facts are obvious. If you know how pieces move in chess, it's obvious that a king can reach every square. It's also true, but not obvious, that a knight can reach every square. So I'm just going to go through some of these examples. Consider a graph with colored nodes. If I tell you that every edge has the property that the two nodes it connects are the same color, and I tell you that there's a path from A to B, then A and B are the same color. So there's a question of how it is that you know that. And there's a simple little analysis in terms of Kleene algebra, certain logical rules of inference having to do with how one defines a path that immediately produces that result. So here's another example. Consider a Swiss chocolate bar. So a Swiss chocolate bar is a candy bar. It's got 3 by 5 little subsquares. I can break it into pieces. And the question is, how many breaks does it take to reduce it to just all the little squares? So when people first hear that problem, they don't know. They start, thinking about ways of breaking it down. And then somebody says, oh, well, every break increases the number of pieces by 1. And suddenly, boom, you see it doesn't matter. It's going to take, n-1 breaks to get that to be n pieces. But the question is, why did that statement that every break increases the number of pieces by 1 lead to the answer? What happens in that snap? If you try to, write a program that does that, you have big problems. So there's idea that there's this notion, there's these things that we just know that are obvious, that appear to be logical truths. Logical truths seem to play a role in our thought process. Logic also seems related to lexical semantics. So, you can give these logical properties of words of English. And I'm not saying that this is the right way to make progress in NLP at this point in our understanding of NLP, of natural language processing. But these are phenomena that are worth keeping in mind. So if I look at a word like give, and if I have an event E, which is A1 gives X, agent 1 gives X to agent 2, then A1 had X before the event, and A2 has the event after, had X after the event. Right? If I give you something, I had it first, then you have it later. And this is related to Davidsonian semantics for natural language and the situation calculus of McCarthy and Hayes. And the situation calculus is something probably worth knowing and being aware of, and Davidsonian semantics similarly. There's another weird thing about logic. Logic seems related to computation. So I asked this question earlier: is Python, is high-level programming in general, telling us something about our cognitive architecture? Is our cognitive architecture, human cognitive architecture, somehow have a good impedance match with high-level programming, functional programming, object-oriented programming? Are they reflecting the way we think? So what I'm going to try to point out here is that logic is related to computation. So logic is related to the things that happen in high-level programming. So in particular, you can use logic itself as a programming language, and it has nice properties as a programming language. So logic programming is tightly coupled to dynamic programming algorithms. So let me give an example. So I want to talk about, I've got a graph, and I want to talk about what's reachable in the graph. What can I reach? And I can write down declarative facts. If I'm at X, then I can reach it. If X is reachable and I can go from X to Y, then Y is reachable. Okay, so these feel like declarative logical facts about reachability. And the observation is that if I can interpret these declarative facts as a program, as a bottom-up logic program, which is just doing inference. It's just taking axioms and closing under all logical conclusions. So if you just take axioms and close under conclusions, you end up with something that characterizes dynamic programming algorithms in general. So this logic program gives you a linear time reachability algorithm just by writing down the facts and just running inference. So logic is related to effective computation. Here's another weird thing. So there's this logic programming language. I write inference rules and I close under the inference rules. I take premises and just everything I can deduce, I deduce. And for certain classes of inference rules, that closure terminates quickly. People are used to saying, well, logic runs forever. It's, and it's recursively enumerable complete. It's just too slow. There's a class of axioms that when you run inference terminates. And that class of axioms that when you run inference terminates gives you what's called a descriptive characterization of the complexity class P, the set of polynomial time programs. So there's this restriction you can put on these inference rules that says that if in an inference rule you require that every term, everything mentioned in the conclusion of the rule was also mentioned in some antecedent. So I call that a local rule. That a logic program having that property, that it never introduces new terms, the inference will run and terminate quickly because it never introduces new terms. And you can show that that programming language, subject to that restriction, defines all and only polynomial time algorithms. Fun fact, it's called descriptive complexity theory. Okay, I'm going to end on current attempts at unifying logic with the current state of AI, deep learning. So the first thing I'm going to talk about is I'm just going to have one slide on that mentions the Math0 program. So this program asks, can we do for mathematics what has been done for Go and chess and shogi? Can we build something that through self-play learns to become a superhuman mathematician? This is the program that fascinates me at the moment. So all of my research thinking, other than teaching this class, is going into thinking about this Math0 problem. Christian Szegedy at Google is big into deep learning. This is a deep learning person. He's responsible for adversarial images, pictures of butterflies that get, with little tweaks, you make the system think it's an ostrich. He was on the first paper on batch normalization. He wrote this very prominent early vision network called the Inception Network. So he's very much a deep learning person. And he just wrote this paper focusing on something he calls auto-formalization. So this is the problem of taking mathematics papers, and they're always written in English. And it's important that they're written in English, and I'll talk about that in the next unit. And taking English papers and translating them into formal formal language with precise semantics that can then be formally verified. And so he's calling this auto-formalization, and there are good reasons to believe that this auto-formalization is a powerful problem in the sense that there's lots of bootstrapping opportunities. The translation from the natural language to the formal representation has to satisfy the constraint that the thing that comes out is true. And if you've got a good reasoning system, you could test truth, and the test of truth can guide the translation. And then once and the translation is also, you're also able to translate proofs. So your ability to determine if something is true is going to be boosted by your ability to read proofs. So there's lots of bootstrapping opportunities in this auto-formalization problem. So Christian Szegedy is also of the opinion, and he also views this as a path to AGI. So he shares with me the belief that if we're really going to get to AGI, we need to get to something that can at least do logic and formal reasoning. And how we get there is a whole nother, it's probably almost certainly going to involve deep learning, but we have to get there. We have to get to something that can do real logical mathematical reasoning. So I've got one more unit on AGI focusing on natural language. We'll do that next.